I can see that you can see my screen, and I am monitoring chat as well. So if you have any questions as we go along, I will type them in. I should be able to see them. Yeah, arrange my screen so I can definitely see the chat. Okay, so last time we stopped at a very simple example, but as I said, like in terms of intuition, it's a very useful example of Bayesian inference, which is simply inferring proportion or estimating proportion of something unknown event in a population. An example we used was the number of individuals who were positive for, let's say, COVID-19, and they experienced that infection. But that could be anything, of course, anything you want to estimate. When people do polling for political campaigns, it's the same thing, right? So they collect the data the same way, and the outcome is also binary, or it could be more complex, but could be just binary, whether someone is going to vote for the candidate or not. Okay, so today I want to start with the general setup, and then I give one example just so that we can practice like how to formulate a standard sort of or non-so-standard problem in statistics from a Bayesian point of view. And then we'll move on to some algorithmic questions that we need to address. So Bayesian inference, generic setup, right? So we start with some vector of data. And it doesn't have to be a vector. It could be a matrix or a tensor. That's not important that it's a vector because everything can be vectorized. So it's sufficient to say it's a vector. So just some numerical object that collects all our data. Even if you work with unstructured data like text or video or images, they still typically would be digitized, and you would use some embeddings to convert words or phrases into numbers and so on. So we have a vector of model parameters. So for example, in our case, where the simple example, we had theta was our unknown proportion. That was our population proportion or probability. So, I will be using that. I noticed that I haven't been using it before. I probably will be using it just by habit. So I just want to address it from the very beginning. That maybe not so super common everywhere, but EG means, for example, it's abbreviation of, for example, in Latin. I don't speak Latin. But I think it's exempli gratia in Latin or something like that. But we use in scientific writing this a lot in terms of EG. That just means, for example, just because we're lazy to write it out. Density probability, we need another object. So P, Y given theta. So density and probability defined by the data generating process or model. So we need to have in mind some conceptual understanding of how our data are being generated. And that's a little different from classical statistics. A lot of times we do have that as well, but not always. A lot of statistical machinery could be go in the direction of like, okay, I don't want to model my, to have a model, and I want my inference to be as much, robust as possible to model my specification. That's why I don't want to specify my model. In Bayesian inference, we do specify our models. We just make them very flexible to avoid model misspecification. So for example, in our case, we had probability of Y given theta in our little example from last time. That was simply a binomial probability mass function. But it could be a very complex object as well, and eventually we'll get there. But right now, example from last time was a binomial. And we also need priors, right? So density of the prior distribution that encodes our prior beliefs. about data. And I will when I put a bar on the bottom, that means it's a vector. So for example, in our case, we had one parameter, not a vector, just one scalar parameter, and we used beta density in last lecture, right? So just to remind you, in terms of what we had in terms of examples. All right. So the output of the Bayesian inference is would be posterior distribution of model parameters, which is we can always write out in using the Bayes rule that we covered last time as our data generating model likelihood, P of y given theta times the prior, and then on the bottom, integral of the same object as of a numerator, because this integral exists because we need to normalize, because densities need to sum to 1. So this is just a normalization constant, which turns out to be also important for many practical tasks. But right now we're not going to talk too much about this. So this is our posterior density of model parameters. Yeah, I see a question about the likelihood. Let me finish writing. Yes, so the likelihood is determined by, so this term right here, that's our likelihood, P of y given theta, that's determined by the data generating model. So anything we assume, we should be able to derive this likelihood. Sometimes it's really complex. Sometimes this likelihood could be intractable, and it's also, there's methods for dealing with that. But ideally, we would like to be able to compute this object for any combination of y and theta. I would like to be able to write a function in my code to return a value, a real number, a positive number actually, but because it's a density. Okay. So this is generic setup. This is our inputs, data, some model that we believe is reasonable. Again, we can test it and then reject this model and say, nah, that's not good. Let's move to something more complex or more flexible. But we need to start somewhere, and then we have priors. And notice the main difference that we're treating parameters as random variables. In classical or frequency statistic, we don't do that. Parameters are unknown fixed quantities that would like to estimate. We don't really think that parameters are random, to be honest. It's a convenience. It's convenient for us to encode our prior beliefs in terms of distributions, in terms of probability densities, and in terms of a prior distribution. So really, we're thinking about that our knowledge is kind of uncertain about the parameters, but we have it. So that's why we want to somehow codify it using mathematical machinery of probability. Okay, so in practice, we use the following summaries. This is kind of all abstract, and last time we stopped at this, and we kind of stopped at this picture right here, right? So this is the example that I gave about binomial proportion. These kind of blue or magenta line is a prior. So it's kind of shallow, or sorry, maybe not shallow, but wide. But it says that roughly we believe our probability live between 0 and 0.2, or maybe between 0.05 and 0.2 more. A lot of masses there, but close. It could be 0 as well. And then we converted data, basically with data, we converted this prior belief into posterior belief, which is these red densities. But it doesn't really, I didn't explain how we use them in practice. So let me just spend a couple of minutes on that. So in practice, if you want point estimation, just point estimate, and you have a number, you want a number, okay, like what is this proportion? You actually have a couple of choices, and they sometimes give similar results, but it's important to remember that you have choices. So you can do either posterior median or mode of the distribution, or mean, posterior mean of this distribution that we just postulated as our main object of interest, posterior distribution of theta. For example, you can say, okay, my theta hat, my estimate will be as a vector, so it's a vector estimate, will be expectation of theta given y. So it will be this object right here. So this is our posterior mean. Point estimation is not particularly interesting to us usually because this is an arbitrary number, and it's the most important part actually is uncertainty. But sometimes you need a number, maybe just to run with it and do something with it. But in many cases, you want to understand how uncertain you are about this parameter. But let's, for example, work out the point estimation for, as a first example. So in our previous example from last lecture, we saw that beta distribution was the posterior of theta given y, and the parameters of beta combined our prior knowledge, which is these alpha and beta, where that's how setting those numbers to 2 and 20, we got this magenta curve, and that's how we encoded our prior knowledge, and y and n were our data. N was the number of samples we took, which was 100, and y was the number of successful samples, or successful in quotes. In that example, it meant individuals who tested positive for antibodies against COVID-19. So if you go to Wikipedia and look up the properties of beta distribution, you'll see that the mean of the beta distribution is the ratio of these parameters that go in shape 1 and shape 2. So in this case, one of them, so it's a ratio of the first parameter of beta, which in our case, in our posterior is alpha plus y, and on the bottom, you put the sum of these two parameters, which in our case is this. And you see that you have this elimination of the data of y, at least on the bottom, and you have alpha plus y, alpha plus beta plus n. And so you can sort of isolate, like, this is your prior contribution. And so the reason I'm highlighting is because, a natural estimate of proportion is just a fraction, right? Y over n, this is very natural. It's both maximum likelihood estimate. It's also method of moments estimate. You can formulate it any way you want. But if you don't know anything about statistics, and you tell me that 10 people out of 100 got positive tests, any reasonable person with some numerical literacy will tell you, okay, so that probably means 10% of the population had COVID-19, right? That's my estimate. It's just 10 over 100. This alpha and beta provide prior if the numbers y and n are high and alpha and beta are relatively low, then it really will be approximately y over n. But in case of data sparse, and alpha and beta more higher, kind of more informative, then it will have some influence. So that's the kind of an example where you can clearly see how data is combined with the prior information to get something reasonable. So, for example, in this first hypothetical data set, when we got 0 positives, so if we plug it in, we get 2 out of 122, which is approximately 0.116. And notice that's actually the part where the classical inference would have trouble with the 0, because it's hard to estimate probabilities of rare events, frequencies of rare events. So 100 samples is not enough to estimate something small. And so your classical inference would give you a point estimate of 0, which is kind of not reasonable because nothing is really 0 ever. The reason we're doing this is probably we believe that our event has some maybe small probability, but not 0 probability. In case of 10 out of 100, right? So this is a different scenario where we got 10 out of 100. We will get 12 over 122, and that will be approximately 0.98. So this will be approximately our 10% that we sorry, what? No, that's something. Hold on a second. I did something wrong here. I don't know why I wrote this. What is 12 over? Yeah, I missed 0. That's right. Okay, 998. Okay, that's the correct one. So it is our basically 10%. but slightly less so because again, our prior was maybe had some mass near zero. Oh, sorry, I missed the question about a couple of minutes ago about where elaborate where the integral comes from. Do you mean which one? I wrote a couple. Do you mean this or this? Posterior mean. Oh yeah. So we actually will talk about that in a second. So this integration comes from just definition of the expectation. So I will go over that. So maybe hold that thought for a second. I'll remind you about the expectations in a second more specifically. So if that's not clear, don't worry about it right now. But the basically, we want some sort of measure of centrality of these distributions. So there are multiple ways to measure centrality, like the center of the distribution. So one of them is the mode, which is the highest point, right here. This is called the mode, the place where you achieve the highest value. That's also a measure of centrality. It could be the median. The median is the place where you kind of divide the distribution exactly in half, so that area under the curve to the left and to the right will be exactly 50%, right? So that's median. And the mean is sort of which is this integral is basically weighted average of where instead of summing, you're doing integration, but think of it as a weighted average. I'll go over it in a second. So, okay. So this is point estimation, but as I said, in many cases, especially in sciences, but I would argue everywhere, we would like to understand uncertainty, like how uncertain we are. And so the way we do it is we do it with Bayesian credible intervals, which is an object which is analogous to frequentist confidence intervals. A lot of times they do end up very similar, but not always. And we usually do it for univariate parameters, so scalar parameters. Even if I have a vector, I'll do it one by one. It's possible to do it jointly, but in terms of interpretation, it's so hard that no one is doing it in practice, to be honest. So what you do, you take every theta I, right? So you have theta, which is a vector of parameters. You take one element of that vector, and you form quantiles. So I'll elaborate on that in a second. So notation-wise, I'll do this 1 minus q over 2. I'll explain in a second what I mean here. So where these two numbers, this is the interval, where the probability of your theta I being less than this quantile that I just described, q over 2, given y is q over 2, right? So this is a special number, basically, that, like, for example, the way I drew this part right here, so that this is probability. So if this is the way I drew it, it was theta. In this case, we don't have any I because it's one parameter model. And the Q I used was 2025, which means that this area under the curve right here is, if you calculate it, should be 0.25. Which gives me the probability that theta is below that number is 0.025. And the other one, the other quantile is defined the same way, theta minus theta I1 minus Q over 2 is 1 minus Q over 2. But also that means also that theta I above, so it's basically, or equivalently, theta I will be above that number, will be Q over 2 as well. So, right, so this is a right-hand tail probability of the distribution. So hopefully, let's work through that. I know it may be notationally a little bit strange. Let me also point to these things. So these are called posterior quantiles. So these are just quantiles of our posterior distribution, posterior quantiles. So let's work on a couple of examples so it becomes clear. So I want a visual. If we have two samples that make some difference, sorry, I just noticed the question. If we have two samples, does it make a difference whether we compute the posterior one by one or we combine samples in one sample? By two samples, if you mean the data, two samples, like we've collected data twice, sampled once and sampled twice. If we do sequential inference correctly of Bayesian inference, basically have the prior updated, then collect another sample, use our posterior from the first sample as a prior, analyzing second posterior, it shouldn't matter if you do it jointly or in a sequential way. But there's no particular reason to not to combine if you have them both, unless you believe there's something different between the samples and you need to model the differences. Okay, so if I use this example, y is equal to 0, n is 100, alpha is 2, beta is 20, right? It's exactly our setup from the previous lecture. Then this will give us what's called 95% credible interval, which is the one mostly used because people think 5% and 95% are magical numbers for some reason, but that's okay. We need to agree on something, and so that's usually agreed upon. Why it's 95% credible interval? Because notice what's happening. So if I, for example, so this will be the quantiles, this 0, 0, 2 in this case, and 0.45. So this will form this interval in this case, and my credible interval will be this vector with two components, right? Two endpoints. And what it says is that according to our posterior distribution, notice if these inequalities are correctly specified, the one that I wrote, this one and this one, that means that posterior probability of theta falling between these two numbers is 95%, right? Because I have 2.5% on the left, 2.5% on the right. So in the middle, what is left is 95%. So that means that my posterior, so basically my posterior belief now about this parameter, that it should be somewhere between 0.0002 and 0.045. How do you feel about that?
Can you try to connect those numbers 0025, 0975 with the plot which is there?
So let me see. So I'm not sure I understood exactly the question. So you mean these two numbers connected with the plot? Or
Not
no,
those.
or
Not those. We're interested in those quartiles.
quantiles, yeah, quantiles.
Quantiles.
Quartiles, you're right. Quartiles are specific quantiles which are 25 and 75%. But yeah,
Yes.
so what you wanted to connect. So basically what's happening here is that if you take the integral, 1 second. If you integrate this part and this part, there's a tiny little things, right? So this part will give you 0.025, and this integral, its area under the curve will be 0.025. So that means that whatever is left in the middle, right? So this whole thing between these two numbers, which I'm gonna put in green, so that's 0.95. So these quantiles are specific numbers that you find. They're basically solutions to integral equations, right? You try one number, you do the integral, it's like, okay, that's 10%. That's not good. Let me move it. So you kind of numerically solve for these numbers until you get exactly 2.5% mass on the left, 2.5% mass on the right. That means 95% is left in the middle.
That's clear now. Thanks.
Of course. Yeah, you can use CDF. There'll also, I'll show you. Yeah, so these numbers will be, Mikhail is asking if you can use CDF. Yes, you can use CDF to find this exactly CDF. In R, you can type Q beta, for example, which we will do in a second in exercises and in the code, and it will give you the numbers. Yeah, but this has to be done numerically. There's no, if you go to Wikipedia of beta distribution, it will not give you all the quantiles of the beta distribution, but you can find them numerically. Good questions. Thank you. Okay, so if we do the same for for our example, when we had 10 out of 100, right, just to give a different example, then I will have this theta 0.025, theta 0.975. These quantiles came out to be 0.025, for example, and 0.17. So if I put them, let me try to put them on the same plot so you can see. Yeah, no, it doesn't quite work. Sorry. I'll have to scroll a little bit. So this theta that I just pointed out here, so that ended up being 0.052, and that number is 0.157. So we're saying basically, right, so in this case, when you have 10 out of 100, yes, the point estimate is 10%, but 100 samples is not enough to estimate that precisely. You're not sure it's 10%. What we can say, it's somewhere between 5.2 and 15.7%. That we can say. But notice there's quite a bit of uncertainty. We're basically saying it's somewhere between 5 and 15. And yes, the center is at 10, but it could be 5, it could be 15. We cannot guarantee it's 10%. So that's the most useful part of any statistical inference, classical or Bayesian, being able to quantify uncertainty. Because again, point estimates without this uncertainty are quite useless most of the time. What's useful is to understand these intervals, like how uncertainty intervals. So frequency statistics use confidence intervals, and Bayesian statistics use credible intervals. And that's exactly on the bottom that I wrote before, the answer to Mikhailo's questions, how these quantiles are computed. And yeah, this has to be done numerically, these calculations. Like, for example, Q beta function in R will compute CDF of any Q beta, Q normal, whatever, Q norm, sorry, whatever distribution you're using, this Q plus the name of the distribution will give you these calculations. All right. Okay, so this is in practice, that's what kind of we wanted to. So our inputs are these model data, parameters, and so on. And then on the output, we have posterior distribution. But in practice, plotting this distribution in high dimensions is not going to be practical if your number of parameters is 100 or 1,000, or in this, in our age, number of parameters could be millions of billions if you're fitting some really complex models. But if you're interested in something very specific, like most of the parameters are nuisance. What nuisance means, they're not interesting to us. But we have only a couple of target parameters. You can isolate them and compute these intervals, uncertainty intervals. Okay. If you are ready, we can move on to an example, something that you have seen probably in your mathematical statistics or other classes, which is multiple linear regression, right? So this is bread and butter, so to speak, of statistics, where the premise is you have your response variable y, something you're interested in predicting maybe, and then you have your design matrix x, which has for each, let's say, individual, maybe each y could be, maybe like blood pressure from an individual, and x could be age of the individual, maybe some other characteristics, age, biological sex, maybe some other markers of that individual, the lifestyle encoded in some, like how much they exercise every day, whatever. And so this is features, called features in machine learning. In statistics, we usually say covariates or predictors. And then the goal is to build a model that given X predicts Y. And the simplest model is this multiple linear regression, right? So in our data generating model, we would say, if we're working with regression, we would say, okay, so the simplest way to do is to say yi is a linear combination of these covariates. So you say beta 0 plus beta 1 x I1. So that's feature 1 from individual I, or covariate I from individual 1, plus ... beta p x IP, because we believe we have p features or p covariates, plus some error where we think that the error term, actually all of them, let me write not just one, but all of them, theta 1 up to theta n, sorry, not theta, epsilon, I'm sure I say theta, are IID, right, independent and identically distributed as normal distribution with mean 0 and variance sigma squared, right? So the noise is just some random perturbation of the of this. Or in the vector form, like if we denote each xi as a vector, so or in vector form, which will be easier for me to write later, more compact in vector. You can also use matrix form, but I think for us vector is sufficient. We can write yi is equal oops, dot product of xi vector and the beta vector plus theta I. That's so just, vector. My vectors typically would be column vectors. So xi transpose is a row vector, beta is a column vector. You multiply them, you get a number back. That's your inner product. And so the parameters, the vector beta is just this vector beta 0, beta 1 up to beta p. And another parameter is sigma squared, right? So we have p plus 1 betas plus sigma squared, which is our variance of our noise, right? So this is nothing is Bayesian here, right? By the way, right, this is pretty classical. In the only part which is we have to be explicit, and sometimes in classical statistics you don't have to be. We're assuming normal distribution. For linear regression to work, it doesn't have to be normal. It's as long as it means 0 and you have enough samples, you can rely on asymptotic results, and that will be fine. But when we're Bayesian, I need to actually to specify full model. So that's why I'm insisting on normality. We could use t distribution, we can use something else, but we need a distribution. Are you with me on sort of regression notation? Any questions before we move into sort of Bayesian formulation of that? Does it look familiar? Morbid silence could mean two things. Either you're confused or you're bored. But unfortunately, the third possibility, which is both, confused and bored at the same time, which is my least favorite when I lecture. Anyway, let me know if you have. Oh, okay, I didn't see thumbs up. Sorry. Somehow um, when I minimize a little bit my Zoom probably, so I don't see thumbs up. Oh, that's a bummer. I want to see thumbs up. Uh, that's exciting. Um, So yeah, so Mikhail is asking about sigma. That's correct. In classical regression, sigma squared exists. You can get it. We rarely look at it, but when you compute all of these, R squared and other things about regression, you are under the hood calculating basically it's your sample variance of your residuals. So if you have, if you get your residuals, you can get the sample variance of those, and that's estimate of sigma squared. We just don't explicitly usually formulate it in a classical setting, but it's there. But when we're Bayesian, we have to be very clear about all the parameters. So that's why Bayesians are actually more explicit in many ways. That's just by nature. So we don't sort of brush anything under the rug. But it's a good question about sigma. Okay, so the likelihood. So okay, remember our next component is the likelihood, which comes from our data generating model. In our case, our likelihood is density of y, our response, given our parameters beta, vector beta, and sigma squared. We usually assume independence. You don't have to, but the classical setting, or the simplest setting, I should say, is that we assume that yi's are independent from each other. So it's our independence assumption that leads to the fact that this is just a product, right? If you have independent random variables, you can just multiply their densities. The same with events. If you have independent events, probability of that they occur simultaneously is a product of individual probabilities. The same thing works for random variables. And so you get product of yi densities where each individual term in this product is a normal density, right? So I'll just write it out so it's clear. But that's just your normal or Gaussian density, right? So of a Gaussian or normal distribution. But I just wanted to be explicit that, okay, we can compute it, right? So if I can compute each of these for each of my subjects from whom I measured something, I know by I know xi. If I know my parameters, beta and sigma squared, I will be able to plug them into this little formula, multiply the, n times everything, and I can compute my likelihood. That's very important to me that I can compute stuff. So in mathematics, when I read mathematical results, I actually always separate results which are computable from non-computable. Because if I have a high dimensional integral as a result of a theorem, that's great, except if it's not computable, I cannot use it. So I can only admire it, but I cannot really use it in practice, and I cannot kind of code it up. So if you are trying to do something, if you're implementing something, it's really important to have an eye on this. Like, is this mathematical result something that I can actually code up, or this is for admiring and then maybe working on it later, maybe trying to compute it later and developing some new algorithm to compute it. Um, Priors, there are lots of choices. I will, to be honest, do something, relatively arbitrary. Uh, you know, and maybe even a little silly, but you can say, for example, okay, I don't know much about these effect sizes in my regression, the regression coefficients. I'm going to just assume they're normal with zero mean because I believe most of them don't matter, and some variance, some constant variance that I'm going to choose. I'm not saying it's the best choice, but I don't want us right now to think too much about it. We'll think about it next week. Constant of our choice. Sigma squared, again, there are lots of the choices. Like you can say, for example, I'll use gamma distribution to tell me something about the noise. Um, People actually don't use gamma. More often they use inverse gamma, which means that 1 over sigma squared is gamma. But again, that's a technicality which is not terribly important for us to worry about. So, okay, so let's recap. I have my data generating model, right? It's a normal model where I combine covariates for each individual. I formulate the mean of that individual response, and then the model is that the actual response is a random draw from a normal distribution with mean equal to this linear combination of covariates and some very constant variance. And then we have priors with likelihood. So we can go and formulate our posterior. Our posterior is high dimensional in this case, right? Potentially, at least. So it's a posterior density of beta and sigma squared. So it's a multivariate density, not a univariate as before. But it's still the same thing. It's a product of our likelihood, which we decided that we know how to compute. And in this case, we'll put the priors independently on beta and sigma squared. So that's why I'm going to just multiply them. We could put them jointly on this, but it's hard. So to be honest, I don't know how to put a joint prior on beta and sigma squared in an intelligent way, encoding my prior beliefs about both. So I never do that, but mathematically it's possible. Yeah, so Georgi is asking or commenting that in Bayesian inference you can start from a non-existent prior like uniform distribution over R. Well, so if you uniform distribution, right, it's not a proper distribution because it's not gonna not normalize to 1. So it will not. That's something which is called improper prior. Like proper prior would be like the actual density that normalizes to 1. If you put the uniform distribution of the whole real line, the integral over the area under the curve is infinity. So it's not a distribution. So technically speaking, it's not allowed even to do. You have to have something which is properly integrates to 1. But you're right that people do that sometimes. The problem with that, you need to prove before you do that your posterior will be proper distribution because you don't want your posterior to be a non-existent distribution. So it's a kind of dicey path, like a little slightly dangerous path to go on, and some people do, but I do not recommend to go there initially. So does it make sense? So prior distribution, like uniform distribution over 0, 1, that's okay, right? Because that integrates to 1. But uniform distribution from negative infinity to infinity, that could be problematic because that's not a distribution, actually. That's not real. Um, okay, bad news. Bad news is that what we just saw is that Bayesian inference requires calculating high-dimensional integrals. And good news is that like this one right here, right? So for example, like this is I need to do this integral on the bottom. If I have even 10 betas, right? I have a very simple regression with 10 covariates, so 9 covariates plus intercept and sigma squared. I don't know how to integrate functions which, in 10 dimensions. We have a couple of tricks to do it analytically, maybe 1 or 2, maybe 5, but we don't. If we have a non-standard distribution and density, which is not like known to us, it's not in the Wikipedia, it's not a normal distribution, it's not Wishart, it's not multinomial, whatever. We don't know how to integrate analytically almost anything. Analytic integration exists only unfortunately in our very simple calculus courses, but in real life it never happens almost, right? It's like very few examples. So we need to do the integration numerically typically. Um, Good news is that we have algorithms for that. And that's something we need to talk about next. For the same reason, when you start working with differential equations, or partial differential equations, God forbid, you quickly will realize that none of them are solvable. Like the only examples that analytically solvable you already have seen in classes, and that's it. That nothing else exists. So that's everything else needs to be done numerically. Because again, solving ODEs or PDEs, it's the same integration, just different perspective. Um, okay, so one of the ways to do numerical integration is called Monte Carlo. And so before we go there, just a quick reminder, and that was already a question from Mikhailo about expectations. So just a reminder, mathematical expectation in case of discrete random variables is defined more maybe naturally, is just a weighted sum. So if I have a x as my random variable and I want to integrate find the expectation of some transformation of x. So it could be x itself, it could be x squared if I want second moment. So g is just some function you apply to your random variable. Then the expectation is a weighted sum where you weight the values, all possible values of this function by their corresponding probabilities, right? So it's just a weighted average. If you, in continuous case, you replace sum with integral, but it's the same thing. You weight your function with density now, and you integrate between negative infinity and infinity, or something else if your domain is not all real line. If it's a beta distribution, you would integrate from 0 to 1, because your density f will be 0 everywhere outside 0 and 1. Okay, so this is your expectations. And so, just again, to remind you, like, exponential random variable, for example, has this density which exists only on a non-negative real numbers, and lambda is your parameter called rate parameter. So in this case, you would compute, for example, expectation of x as this, well, technically from negative infinity to infinity, but you immediately notice that this, because of the indicator function in the density, it's really from 0 to infinity, x lambda e to the negative lambda x, and then you do integration by parts, which I will not do. right now online. Integration per parts will give you 1 over lambda eventually. So the expectation, so that's, mechanically, that's how you can compute expectations for simple things for which you can do analytic integration. So the Monte Carlo is really is just a way to use the strong law of large numbers. There's nothing more to it. So if I have potentially infinite collection of random variables which are independent and identically distributed with finite expectation, then the law of large numbers says that if I take the empirical average, right? If I just take arithmetic average of these numbers or these random variables, that and I send it to infinity, this limit will be my mu, my theoretical expectation, right? So, and basically, what strong law of large numbers says that informally, if you average empirical averages converge to theoretical averages, that's what basically it says, and that empirical averages of IID random variables converge to theoretical one, converge to the theoretical average, which we call expectation. Okay, sounds familiar? Law of large numbers. If you average, good things happen. Monte Carlo integration basically says, okay, now if I have an integral, maybe an expectation, then and I want to estimate my expectation, or if it is discrete or continuous, if I produce random realizations of some from a distribution with density f of x, and I have expectation of one of them or all of them less than infinity, then basically what strong law of large numbers will say that this hxi will be approximately my expectation that I want. So if I don't know how to do analytic integration, I can just generate random samples, average them, and that will give me something that I want, right? So that's all. So you can form basically like this, we will call this will be our numerical estimate of an integral. So this we sometimes call it HN bar, right? So this is just to emphasize that this depends on the number of samples that we draw. So if we are not happy with it, if that's not too accurate, we can increase number of samples and we can improve our estimates or our approximation of expectation. So for example, in the second moment of the beta distribution that we worked out already, so this is exactly our setup that I just talked in the beginning of the class about, right? Prior is beta with 2 and 20. Data is 10 samples out of 100. Posterior becomes beta distribution 12, 110. Well, suppose I don't know how to compute the second moment of that distribution for a second. In this case, we can derive a formula and it exists. You can go to Wikipedia. Well, actually, the second moment in the Wikipedia does not exist, but you can derive it from the variance in the first moment. You can derive the second moment, which is what I did when I was doing this lecture notes. So we know that you can compute this sort of analytically. You have an analytic formula that tells you what the second moment is. And so in this case, we know that if you plug that in, then the expectation of theta squared given y, our posterior expectation will be, these 12, 12 plus 1, which will be something like 0.01. But let's pretend that we don't know how to do it, and let's try to get the same number using Monte Carlo integration. So our game plan would be to generate random samples from theta 1 and theta n from a beta distribution. And then return. And in this case, I'm going to square them because I'm interested in the second moment, not in the first moment. I'm going to draw m samples. So because we're already using n in this example, n is a sample size for the data. M is the sample size for the number of iterations I'm going to do Monte Carlo iterations, Monte Carlo samples. And that should be approximately equal to my posterior expectation. So the second moment is a question from Vladislav about the second moment. The second moment is really used to, if you combine first and second moment, you get variance, right? So that's kind of the main application of it. So you can go to variance directly, but it's a little easier to conceptualize that if you have first and second moment, you can combine them to get the variance of the random variable. Anytime, yep. Okay, so let me switch real quick to, I have only a couple of minutes, but I want to use them. Um, so I posted already on GitHub a little demo. So this code is already on GitHub, so you can download it. So first of all, when you work with, so this is Quarto document. Again, if you're not familiar with Quarto, you don't have to know this, but it's just a way to combine text, code, and math and everything together. So you have a document which combines everything. And so this chunk of code basically sets the seed. Setting the seed is important for reproducibility. When you work with random algorithms, you want to be able to make sure that you can reproduce if you have bugs or whatever, some problems. So we don't have to set the seed here, but I'm setting usually the seed just in case. So here, this is our setup, right? So this is our prior number for beta distribution 2 and 20. This will be for our beta. This is our data, 10 out of 100 samples. This is our posterior, which is a combination of data of these four numbers, basically. So I'm just going to put them in. This is the theory tells us that the second moment, actually, this is a typo. Should be squared. The theory tells us the second moment of beta distribution is this formula. And so we can go and plug it in. And so that's the 0.01 number that I gave you in lecture notes. So this is basically without using any integration, just knowing the theory of beta distribution, theoretical properties. You can also do it using deterministic integration, right? In R, there's a function called integrate. You give it a function, which I defined right here, which is defined as x squared times the density of beta, d beta is density of beta, and so on. And you can, in this kind of two lines of code, or maybe a little more, you can compute the same number, right? So as you see, it says 0.01 here, the same deterministic integration, which is basically, trapezoid rule on steroids. It's a little better than trapezoid rule, but it's something like trapezoid rule when you practice calculus. And it gives you the error term. Now we can do Monte Carlo integration. So Monte Carlo integration, for example, I can say, okay, suppose I draw random samples and you use our beta function to do that. So we're going to draw 1,000 samples from a distribution with parameters given by our posterior formulas that we defined already. And I'm going to return mean of these samples, but I'm going to square them, right? Notice I'm squaring them. So that's exactly our game plan that we wanted to do, right? We're going to generate a vector of 1,000 dimensions of random samples. and we're just going to average, but not the vector itself. We're going to average the squared elements of this vector. And this will give us something like this. Notice they don't coincide, but they're pretty close, these these numbers. So we got somewhere close. It's an approximation. You can also visualize the samples that we drew, right? So our samples, this is your beta distribution, but the histogram of the samples we just drew. So it's approximately should follow beta density that we know that I showed in class, and you have a code for. You can also compute Monte Carlo errors, but right now it's optional. So if you compare these three answers together, right, this is your theoretical, this is your numerical integration, which is the same thing, and that's your Monte Carlo integration. You can actually assign confidence interval to this Monte Carlo integration. I didn't have time to talk about it, but if there's a way to do it, it's in the code, but unfortunately, in 4 lectures, I don't have time for this. So I'm gonna admit that, and this will be optional. But notice what happens. We can, this is this number, but if I increase this number of iterations by 10 and I rerun it, my histogram will become kind of smoother and better, right? I have more samples, so I have a better approximation. And if I now compare all of these three answers, notice I'm much closer to the very accurate answer that I got from numerical integration or from theoretical formulas. You can also, I know I'm going a little too quickly because I'm running out of time, but I apologize for rushing it a little bit. The code will be available to you, so you should be able to just go through it. Let me actually see. I removed the chat from, well, I didn't remove it, but I don't see it right now. Okay, I don't see anything. Okay, good. Well, I'm not sure it's good, but I didn't miss anything. That's good. You can also do it. You can also do quantiles. For example, right? We talked about quantiles. So this is a way to compute them using numerical integration. For example, this is my median, which is close to 10%. And this is the same numbers I was putting on the screen on my notes, the 2.5% and 97.5%. Remember, we said that if you have 10 out of 100 successes, then you can say with confidence only that you're somewhere between 5 and 15%. You cannot say it's exactly 10. You don't have enough evidence for that. But you can also do the same calculation using Monte Carlo. I can compute, there's a quantile function that computes empirical quantiles, where you basically order your samples and then you cut off 2.5% of them, and that's your quantile, empirical quantile. So you can do empirical quantiles, and they will come out pretty close. Notice that's my 2.5% quantile. This is my 97.5%. So it gave me the same numbers, basically. The reason I'm showing it in this example, it's kind of silly. We know how to do everything analytically, and we don't need Monte Carlo. But in most cases, it's the opposite. We can only do Monte Carlo. And so that's why I want you to practice kind of, and show you what typically we do when we do Monte Carlo. So typically you would do these averages, maybe mean, maybe variance, and also quantiles are very important in Bayesian inference. I'm going to finish in a second. Example 2, I will not go over this, but I just wanted to make sure that it's clear. Even if you don't have any expectation, you just want to compute an integral. Oops, sorry, I didn't mean to do that. Of some weird function, which somewhere I have a plot for that. Okay, let me run it. Like it's just some arbitrary function. You want to compute a definite integral between 0 and 1. You can turn it into Monte Carlo artificially. I can say, oh, but this function is an interval 0 and 1. I can think about it as a expectation of this expectation when U is uniform. And it works, right? So mathematically, it's the same number, but I can write it either as just an integral without any probability involved, or I can artificially convert it into expectation. And if you do that, you can do this numerical integration, or you can draw, and in this case, Monte Carlo. Notice I'm going to draw uniform samples. So before I used beta samples, here I'm using uniform distribution. That's the only difference. So and if you take the average is, this is your numerical integration 0.87, this is your Monte Carlo 0.88, so there's some error, they're not exactly identical. So basically, Monte Carlo is not really only for probabilities or Bayesian inference or anything like that. It's really just a numerical integration tool, and you can try to compute any integral with Monte Carlo by artificially making it a probability problem, a problem about expectations. In Bayesian inference, it usually comes out naturally. We don't have to kind of force it, but you can force it if you want. So in the homework, I'll ask you to do something similar to this lab or this code. So this will be made available, but I'll ask you to do something else with Monte Carlo, sort of by analogy, if you will.